Among the different IoT vertical domains whose security can be enhanced through the use of REWIRE framework, one of them is the smart cities vertical domain, and especially the critical infrastructure scenarios. Due to the distributed and physical dispersed architecture based on constrained on-site components and cloud services, we converge to solutions that are vulnerable to security and privacy risks. A crucial IoT system should ensure the correct operation of the end device and incorporate security measures to protect the entire life cycle of this end device. To securitize the life cycle, we need of a trusted base composed cloud services to minimize security risks, but ensuring seamless compatibility independently of the edge architecture. Leveraging trusted extensions of our traceways, we also enhance end-device operations such as onboarding, secure communications, and access to device resources. But these extensions should also provide protection against on-site attacks, avoiding tampering or physical threats like side channel attacks. In this regard, the REWIRE framework capabilities that are key point for the smart cities use case are the secure onboarding, as automatic device provenance and configuration integrity verification is needed for the strict onboard process, and full update management lifecycle, based on monitorization of events and validation of update packages and involved agents, adapted to constrained environments. All these operations leverage on root secure crypto schemes and attestation policies, vertically integrated in end-device crypto material lifecycle. Odin's use case will evaluate the effectiveness of the REWIRE approach in smart city vertical domains, focusing on implementing REWIRE in critical systems and that ensure the citizen safety. We have specially chosen vehicular and pedestrian traffic systems due to the difficulties managing edge device density. Although controllers have measures in place to protect the device, these measures are simpler for large-scale distributed environments. To simulate this traffic control system, we use the Genesis RISC-V board as a bridge for communication with the Odin's device, acting as the IoT network gateway. The Odin's device acts as a constrained end device that runs the traffic pedestrian crossing control logic and connects with the components. And finally, the traffic pedestrian crossing control, which is an emulation of a four-way roundabout with electromechanical sensors and actuators. The lags of this scenario will be studied and exchanged for a scenario where only the Genesis 2 RISC-V board is used, hosting all the logic needed to control the traffic system and securely communicate with the trust base. In our current environment setup, we use the Genesis 2 board as the handler of all communications between our cloud services and our PLC-like end device. This way, delicate process such as onboarded on the end device with no integrity mechanisms is showcased. Once we proceed with further steps on the project, the control logic and the REWIRE artifacts will be integrated on the standalone Genesis 2, which will securely manage the critical process based on the trust artifacts. For the demo, our environment is based on a real-life example, a four-way traffic roundabout as we previously mentioned. The device managing actuator is installed on an easily accessible utility box. The Genesis 2 board, together with the Odin's device, represents the utility box running the traffic control light. We will showcase a typical onboard and update operations on these remote devices. This way, we can evaluate the different operations on the device and how they affect the real-life testbed. We now proceed with the demonstration video. This is our environment setup. The dashboard simulates a real roundabout located in Murcia. The sensors are connected to the Odinson device, which directly controls the roundabout and manages the events and gathers its own status information. This information is communicated to the Genesis 2, which acts as the outbound gateway for edge devices. In the same way, the Genesis 2 manages the download communications to enable actions such as remote execution of commands or updates on the end device. To monitor the device, the first step is to onboard it on Odin's IoT network and platform. At the top left hand, we can see Odin's platform through which the onboarding is done. At the bottom left, we can see the MQTT messages communicated by all the end devices to this onboard platform. At the top right hand, we have the Genesis 2 terminal. This device will have the MQTT handling module to act as a gateway to the end devices. At the bottom right is the audience end device terminal. This end device has the status communication service, which is currently disabled. When this service runs automatically on boot, the device communicates with the Genesis 2 board, which publishes to the MQTT broker the status of the end device. This is captured by the platform, and from the onboarding endpoint, it detects a new communication device trying to join the network. Once onboarded, the events detected by the end device are communicated to the platform. In this clip, we can see how when the traffic lights are initialized, the Genesis 2 communicates the default status of each sensor. This communication is mapped by the platform and represented visually. For this demo, the status of the traffic light at the roundabout is represented. If a LED is on or off, or, for example, the status of the magnetic detector when a vehicle is above the sensor waiting to enter the roundabout. For smart cities, it's common to remotely update the device in order to add or modify its functionality. In the upper left terminal, we have the Genesis 2 output. The upper right terminal is the audience and device output. And in the lower terminal, we simulate being the system admin, publishing commands toward the end device. Here, the admin publishes the command to initiate the download of the update package on the REWIRE Genesis 2 board. Now the download is currently finished and the package is stored on the Genesis 2. As you can see on the upper right, the audience and device currently has the version 1 of the remote control service. Through a new publication, which indicates the target device, the update package is distributed from the Genesis to the end device. The admin can now, for example, send a command so the end device reports which is the current version of the installed software, now showing version 2. Problem encountered in this scenario, and usually in smart city scenarios, is the lack of security in communications. For example, the communication in this demo are based on the well-known protocol MQTT. The common authentication mechanism in an MQTT broker is a username and password. But this mechanism is very simple and the messages are unclear. For example, in the remote update command, we can see the address of the update distribution platform. So, if an attacker sniffs the network and gets the broker access credentials, he has access to the end device. In the video, any user with these credentials can execute remote commands that affects the traffic light system. REWIRE, through mechanisms such as verifiable credentials and attestations, can be an alternative to avoid relying on simple authentication methods.